All right, so now you did the buffer overflow, like say 202 is the main one, where you do buffer overflow, you gain control of the instruction pointer, and you can execute some code. And the next thing is where we're going to put in code and execute code we added in, which was the classic Alex Null buffer overflow. And like I say, this one doesn't work very often anymore because of data execution prevention, but this is it so you can see it. And so we need to have shellcode to run. That's what they call it. They call it shellcode, or the egg, the code you run, which is the heart of the malware that does whatever you came here to do, usually giving you remote control over the network, a remote shell. You have to have an Intel machine again for what we're doing here. And you have to have address space layout randomization disabled again, which we did before. And then you get this program called ED3A. And I've got it here. So this ED3A, if you look at the source code, this has a main routine here, which takes a command line argument, and then it calls copier on the argument down here, and the copier just copies it into a buffer that's 1,000. That's all it does. And therefore the point is, if the input is more than 1,000, it will overthrow the buffer here. And so you have a buffer overflow. Now there is no code we're trying to execute from the developer though. The previous one we had something called win that we were trying to redirect execution to. Here we're going to inject code, new code, and run it, all from a string. So that's all this does. And so you compile this thing and run it. You run ED3A. It'll tell you need to have a string, so you have to give it something like hello, and then it runs. And all it does is it prints the address of the stack pointer, just so you can see an address to see where the program is, and then done. And the only reason I printed the address is to make sure you can see that address space layout randomization is turned off. This address is not changing. If it was on, it would be a different address every time. So when you do not have an overflow, it just prints done. When you have an overflow, then it'll crash. So the first thing we have to do is make a fuzzer. And so you can do that here. Here's a fuzzer. All this is going to do is you give it a length, and it'll print that many A's. So it's fuzzer 10 and fuzzer 100. That's all it does, give you a string of that many A's. So now you can run that thing. There we go. So it's ED3A. And then, now what a lot of people like to do is they use these backticks to immediately execute a command. I hate that because it's hard to see, it confuses people. I prefer to use the older fashioned notation of dollars parentheses. Does the same thing, but it's easier to print and read and everything. So now we're going to run that fuzzer. If I feed in 10, then it works. If I feed in 100, it works. Remember, we know from the source code it can take up to 1,000. So this is not surprising. 10 or 100 or 1,000 will run fine, but 2,000 is probably too many. Then it crashes. So this is fuzzing. You're trying to find where it crashes, and you might as well get some estimate of how many bytes it takes to crash. So you can try lesser numbers like 1,100, and it still crashes, and say 1030. Oops, get rid of that 0 there. Even 1030 is enough. Even 1020 is enough, I think. Yeah, but 1010 is not enough. Oh, 1010 is anyway, but I think 1020 is a good place to start. So 1020 causes a segmentation fault, and we already know that the injected stuff must be in the last 20 characters. So we don't have to hunt too far to learn why it works. So now we use the debugger. And we can run it on the fuzzer of 1020. And it does crash, and it puts AAA in the instruction pointer, which is what this means. And it doesn't say it explicitly. To see it explicitly, you could do info registers, and you'll see that EIP now contains 4141. And this is real important. When you find a denial of service attack, some of them are not exploitable, which means it causes it to crash, but you don't gain control of anything useful. The easiest one to exploit is where some of the data you put in goes right in the instruction pointer. Now you can attack it other ways, and we'll do that, but this is the simplest exploit. This means some of those characters control the instruction pointer, so that means it'll be very easy to control the operation of the machine. So now we want to find out which characters contain the EIP. So we'll do this EX1. Let me get out of here. All right, and let's cat EX1. Do I have EX1 here? Yeah. So here I make 1,000 characters, and then I just put B, 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 C, 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 D, D, E, F, just the non-repeating characters at the end. So if I run that, that's what it does. The last 20 characters are that, so I can tell which ones of them are ending up in the instruction pointer. So if I debug it again, and then I run it, getting the data from EX1, then it crashes with 45, 45, 45, 45. So that's A, B, C, D, E. It's the E's that went into the instruction pointer. So now I know how to control the address in the instruction pointer. The problem is I don't know what to put there. There's no win function to hit. So I have to make a dummy exploit now. But then eventually we're going to need shellcode, so we might as well make our shellcode. If you have Metasploit, if you have Kali, Metasploit is already installed. If you have Debian, you have to install it, and here's how you install it. I've already done that on this machine. And so here we use MSF Venom. And by the way, you don't need sudo if you're on your own machine. You need that if you're on the Google Cloud. So you can do MSF Venom, and you can list the payloads. There will be hundreds of them. So to simplify it, I'm going to go to Linux bind shells, just looking for those phrases to limit the number of exploits. So let's get out of here. There. MSF Venom is the particular part of the Metasploit suite that makes standalone malware. And in all kinds of different formats. You can make Windows executable, you can make, I think, PHP, all kinds of different malware. And so what I'm looking for here is Linux malware that will make a bind shell, a TCP bind, where it will start listening on a TCP port, which, like I mentioned last time, is not the most powerful exploit, because listening on a strange port will typically not work. The firewall will block it. What you usually want is a reverse shell, but that's a little bit more tricky to set up, and I don't start out with it. So anyway, it runs kind of slow, because I think it's written in an interpreted language like Ruby or something. So it's not optimized for speed. But it will eventually cough up the payloads that are available, as you see them down here. And the one we want is this one, Linux x86 shellbind TCP. That's just the simplest listening shellcode. So it's taken too long here. I'll just go on with my instructions. So here's the one that makes the particular shellcode we want. And if you list the options here, then you'll see what options are needed. And the reason I like it is because nothing further has to be specified. It's going to listen on all interfaces on the target on 4444, and it doesn't need to know the remote address or anything. That's why it's the easiest to use. And it even has a default port of 4444, which, by the way, is also not a good choice for real pen testing, because people have learned to listen. Anything you listen on 4444, we're being attacked by Metasploit. Don't let that happen. So at least you would change that to something else. But in our case, it doesn't matter. So now we can make the shellcode. And this is what makes it. You specify MSF Venom. This is the attack. And then I changed the local port on this one. It turns out, and then I just make Python. You can output it in various formats. So if you do that, then you'll get the Python code. And as you can see, the Python code is just the buffer. This defines a binary buffer variable that contains the assembly code in hex. So that's what I say. This is a raw hexadecimal attack, but you don't have to write it yourself. Now, actually, writing shellcode is pretty complicated. And there's a book, Generating Shellcode, that I think I've got. Yeah, this one here. This is the classic book. This is pretty hard to read, and this task is pretty hard to do, because if you compile assembly, it's all full of null bytes. So you can't have null bytes in shellcode because you're typically putting it in a string, and a null byte will terminate the string. So writing assembly code that does not have any null bytes is kind of tedious. You have to take, one thing you often have to do is take the 64-bit instructions and turn them into 8-bit instructions, so they don't have null bytes padding. And it can be done, but that's why it's nice to let Metasploit do it for you. Metasploit will generate the shellcode that doesn't have that problem. All right, and so anyway, that's what happened here. So it generates the shellcode, and now you notice here, if you don't tell it to avoid, it is going to have null bytes sometimes. So if you want to limit it to not have, and by the way, null bytes are not the only forbidden characters. If you think about it, I'm going to be feeding this into a command line argument in bash. So a tab, a space, a carriage return, a line feed would all terminate the string. If they happen in the middle of it, it won't go in. So there's a bunch of characters you want to dodge. So if you have enough room, now I know I have like 1,000 bytes anyway to work with of input. So 382 bytes is the minimum size. You can encode it to avoid pattern. That will make it longer. But the simplest encoding is to use alpha mixed. that will use only uppercase letters, lowercase letters, and numbers. So you'll definitely not break the string, and that makes it bigger. If you run it that way, it's now 1114 bytes, but that's acceptable in this case. So that gives you this much data, and now you just have to include that in the exploit, and that should be ex2. So if I cat ex2, there you see. So here is the buffer that came from MSF Venom, and here you build the exploit. And to make the exploit, first you have a NOP sled. This is really important. A lot of Metasploit shellcode will not run without a NOP sled, and you always want one anyway. If you inject code and you try to jump to the start of the code, you will often find that you're off by some bytes, like 10 or 20. So you miss, and if you don't start at exactly the right place, it won't work. So you put in NOPs. NOP is just a command that does nothing. NOP, 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 NOP. So I put in 500 NOPs, and now if I hit anywhere in the NOP sled within 500 bytes of the right address, it will just go NOP, 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 egg. So that's why you do it. Your exploit is much more reliable if you have a NOP sled. And something I learned really the hard way, a lot of Metasploit payloads have to unzip, and they use the first 16 bytes to do that. So if you don't include at least 16 bytes of NOP sled, a lot of Metasploit payloads will self-destruct, and they don't tell you. Here's a fun fact. Shellcode is minimalist. It has no error handling. If you run shellcode and anything goes wrong, it just dies with no clue. For example, if you're doing your reverse shell and it can't reach the command and control server, it just dies. Any error, it just dies, and you don't know what happened. So it took me a long time to figure out why a bunch of my shellcodes were dying, because I didn't include an op sled. So anyway, it's a good practice. Always put an op sled before your shellcode. So then I have, so I put in the NOP sled, I define a suffix. So here's what I build. My attack is the NOP sled, then the buffer that Metasploit wrote. Then I put in the suffix, which is enough padding to reach the EIP. Then I put in the EIP. That's the structure of this thing. And so this is ex2. So if you look at how it looks to run this, this is what it looks like. This is the NOP sled, unprintable NIDI characters. Then this is the, then there should be a bunch of capital A's down here. This is the NOP sled. This is the encoded shellcode from Metasploit, which is like random characters. Then come enough A's to reach the EIP, and then for the EIP, I put in 1, 2, 3, 4. So that's the address. So this is like a dummy structure of shellcode. It has the NOP sled, the exploit, enough padding to reach the instruction pointer, and a fake value to put in the instruction pointer. You have to build it this way because I don't know what address to use yet. I need to use the debugger to find out where this NOP sled is. So that's the prototype that you have, and if you run it in the debugger, you can find it. So we will go to here, which you debug this thing, -q ed3a, and then, right, okay, I'm just doing it. You don't really have to do it this way, but you can. If I do list, then if I do list, say 1 to 25, all right, so here's main, and main calls copier, and copier is where the overflow happens, right here. And when it tries to return from copier, that's when I take control of the box. I've overflowed the buffer, so the return pointer is wrong. So instead of going back up to here to continue here at done, it's going to do something else. So that's why I'd like to know the address in main that called copier. I think, let me see here. Yeah, that's the point. This is where the overflow is. So if I disassemble, right after the string copy. Oh, that's right. That's right. That's how I'm putting breakpoint in. Now I realize. I could have done this in source code in this case, but I'm going to do it in assembly code just to show you that. So if you have assembly code, disassemble copier. Okay, there. So here is, by the way, you can read this stuff pretty easily. You look over here, this is the name of the C library call it's making. So this is the string copy that causes the overflow. This is the next command, so I can break right here if I want to see what happened to memory after doing the injection. So I copy that and I put a break there. If you're going to break at a raw memory address, you have to put in a star. There. Okay, so now I can run. I can put in the data from ex2. All And now it's broke at this point, so now I can examine the memory. I can do what I always do, info registers, to see the stack frame. The stack frame goes from CA0 to D0A8, which is much bigger than before because there's enough room there for a 1,000 character variable and some more stuff. So I just remember this number, D0A8, so I can do X, say 440 hexadecimal words starting at ESP, and I'm going to look for D0A8. And there's several pages of this, and here is D0A8, there. So stack frame is everything above this, and so you look up here and you'll see, here's the NOP sled, all these 90s. Here's the shellcode, all these random bytes. Here's the padding after it, and here's the EIP, where right now I put in 1, 2, 3, 4, and in hex, 1 is 31, 2 is 32, and so on. So this is the ASCII 1, 2, 3, 4. And now I know what to put in there. I scroll back up here and find the NOP sled. I just have to pick an address somewhere in the NOP sled that doesn't have any null bytes in it. And I can jump there. So any address up here would work, like CD70 or pretty much anything. And anywhere in the middle would be fine. All right, and I think I've already, so I have to feed that in EX3. So let me, I'll just copy one of these for comparison. Like this is a good address in the middle. Now let me get out of here and look at my EX3. Q, Y, cat EX3. Okay, and CD90, and when I put it in my clipboard, I found CD10 was good. Yeah, CD90 is good too. There was a long, big 500 byte NOP sled. So I've already built it. This is the address I went for. So instead of putting in 1, 2, 3, 4, I put in this address, FFFFCD90 backwards, FFFFCD90. So now I've made an attack. This should be everything. That's my EX3. And so if I go back into my debugger and I run $ex3, it runs and it never comes back because it did what it should. It branched and started a new listening process. So I need another shell. I'm going to need to leave that running, and I need another connection into my Linux server. So that's going to be SSH student at, at that address, which is there, 192.168.64.9. There. Okay, now I can do sudo ss minus pant l. This will show me the listening processes. And there is a listening process on port 31337. So I could connect to that from any machine. I can do it here. I can do etcat 127.001.31337. And that's my remote shell. If I do who am I, I'm not seeing the process, but I have a shell. And I could connect from anywhere. And that's why you don't generally use exploits like this. There's a lot of reasons. A firewall will block it. You also haven't put in any authentication, so anybody else could come in. So it'd be a lot, there are more advanced attacks. But there's the simple attack to show how it works. And that's the point. That's how you inject code, find it, and run it. The problem is, this is all blocked now. Randomization makes it hard to find the code, and data execution prevention means that even when you find it, you can't run it. Because any modern operating systems, when you allocate a region of memory, you're only supposed to have read or execute, never both. So read, write, and execute. And here, we've written to it and then executed it. And that's not supposed to, it's dub write or execute, that's it. You don't have write or execute at the same time. But some operating systems let you do it. You can do it if you can make API calls in Windows. You can turn on a memory segment that way. And there are systems like the Raspberry Pi 3 that don't do this. Every memory segment is read, write, execute. So it happens, but it's not as common anymore. Back in the days of XP, this was the kiss of death. This is what most of the attacks did. You could just do this to every box, and everybody did. And that's why with Vista, Microsoft put in a lot of defenses and Linux put in a lot of defenses. So this simple attack doesn't work that much anymore. But all you have to do is add some tricks to make it work. Yeah.
Microsoft, you're admin of your machine, and you create a file, and you just attribute, read, write, and
No, it's not the file. You have to do it in the way it allocates memory when you run it, which is in the header, in the PE header. It allocates memory. You call a thing called virtual alloc and virtual protect. These are Windows API calls. And you can call them and allocate memory to be read, write, and execute enabled, but all modern programs avoid that. But yeah, that's the modern terms of, it's not enforced, but a policy that is recommended is that you only have write or execute on all memory segments. And this is why another thing you can't do is you can't write self-modifying code. Now, when I started, I was writing 8-bit assembly code for the X80, for a really old processor. And there are a lot of instructions that don't exist in an 8-bit processor. There's only about 100 instructions. So I got used to writing self-modifying code all the time. There wasn't any write to an offset. There was just write to an absolute address. So I would calculate the address and write the address into the instruction and then run it. Because I didn't know any better. It worked fine. It was only when a real programmer saw this, he said, "You can't do that. That's insane." I say, "Why?" They say, "Well, one of the many problems is you can't print out the code and read it. Nobody can audit it. Nobody can change it. It modifies itself during running." I said, "Oh, I never thought of that, you know." But, and you can't do that anymore on modern operating systems. They won't let you modify the executable code. It's either write or execute, not both at the same time, for a lot of reasons. And this is one of the reasons. All right, anyway, let me stop this video, and you folks can try that.